Okay, here we go. Review of Chapter 3. This is everything from Chapter 3. Make sure you got a piece of paper and a pencil out. I'm going to write pretty fast. I'm going to go through everything. You can pause and rewind and replay this if you want, but it's going to give you an overview of everything we learned before we had a nice long break. So, in Chapter 3, the very first thing we learned is how to balance chemical equations, and that the law of conservation of matter said that from this side to this side, no atoms were created or destroyed. There's the same number on both sides. We take an atom inventory, aluminums on both sides, calciums on both sides, and then the way to do it if you have a polyatomic ion like this is to keep the whole thing together if you see it the same on both sides. And then the hydroxides on both sides as well, because you can see there's OHs here and OHs here. So notice there's 3 of them here, 2 of them here, 2 nitrates here, 3 nitrates here, 1 calcium here, 1 calcium here, 1 aluminum here, 1 aluminum here, so far. So to make this, we've got to do a little guessing and checking to make this equal on both sides. And so I'm going to try a 2 right here. That gives me 2 aluminums. That's going to give me 6 nitrates over here. It's going to make me put a 3 here, so then I've got 3 times 2 or 6 nitrates over here, but that makes my calciums have 3. That means I'm going to need a 3 here to make sure I got 3 calciums here. 3 times 2 means I've got 6 hydroxides over here. I'm going to need a 2 here because I need 2 aluminums, and 2 times 3 gives me 6 here. And there's my balanced chemical reaction with these coefficients, remember, indicating there's 3 calciums, there's 3 of these entire hydroxides, and then that makes it a little easier to balance if I don't have to break up the polyatomic ions each time. So that's balancing chemical equations. It assumes you're good at this in the quizzes and the tests up and coming. Number 1, this was number 0 of review things, is something called molar mass. Molar mass has 6 different names that mean the same thing. They are also known as molecular mass, also known as formula mass, and you can replace the word mass with weight. Then molar weight, molecular weight, or formula weight all mean the same thing. They mean take a look on your periodic table and add them up. So if you don't have your periodic table out right now, please pause the video and find your periodic table, because you'll want to look at yours, because I'll flash one up here every once in a while, but you might want to look at yours at the same time as I'm going along here too. So on your periodic table, you want to look here in the upper right hand corner for each one of these little numbers, and those are the atomic masses, and those add up to give you this thing right here: molar mass, molecular mass, formula mass, for whatever formula or atoms or ions you're adding together. So let's find the formula weight for calcium carbonate. Calcium on the periodic table is right here. It's about 40. Carbon, right up here, it's about 12. Oxygen, right over here, is about 16, and there's 3 of them. So 3 times 16, add this up, that's 48, plus 12 gives me 60, plus 40 is 100. So I have 100, and the units on that are always grams per mole, because these numbers right here, these formula masses or atomic masses on here, are analogous to the number of grams in 1 mole of that particular substance. So you can use the methodology that I gave of grams times moles to the negative ones, or grams over moles like this is okay as well. Number 2, percentage composition. Percentage composition of a substance is always part divided by whole times 100%. So let's find the percentage composition of oxygen in calcium carbonate. To find the percentage of oxygen in the calcium carbonate, we take the part that's oxygen and divide it by the whole thing, and then we'll multiply it by 100. So what's the part? Well, 16 times 3, or 48, right? And then we divide it by the whole thing, which we just added up, which was 100. 48 divided by 100 times 100 is, well, it's 48% oxygen. You could replace this with carbon, and then you'd put a 12 up here, because there's 12 for carbon. Or you could replace this with calcium, and then you'd put a 40 up here, because calcium is 40. And you could find the percentage composition of each item in a substance. Next, we go to converting. This is part 3, or the third thing, actually the fourth thing you should have learned. And this is converting from grams or mass to moles to particles, molecules, atoms, ions, or formula units. To do these conversions, you use the periodic table to go from mass to moles, or you use Avogadro's number to go from moles to particles, atoms, ions, or formula units. Right here is the little diagram that you have on your periodic table, and it gives you arrows and what you should multiply by and divide by for each one of the items. Let's do one quick one. Let's convert 2 moles of calcium carbonate to grams of calcium carbonate, then formula units of calcium carbonate, and then lastly to atoms of oxygen. I'll keep that up here on this side, and I'll do the work over here. So letter A, first we have 2 moles, so write down 2 mole calcium carbonate. Start way on the left-hand side, leave lots of room, put a multiply sign, put a line, put mole in the position where it's going to cancel, put gram as your new set of units. You can look on here if you're not sure how to do it. To go from mole to grams, you put molar mass on the top and grams on the bottom. We already added up calcium carbonate on the last problem, so we know that calcium carbonate is 100 grams in 1 mole. 2 times 100 means there are 200 grams in 1 mole. To significant figures, we'd write 2.0 times 10 to the second grams because there's 2 sig figs in this particular measurement. Letter B, then, formula units. So now we have 2 moles of calcium carbonate. Put a multiply sign, put a line. And to go from moles to formula units, we use Avogadro's number. So we'll put mole in a position where it's going to cancel. We'll put formula units, form unit of calcium carbonate. Some people call these molecules when they're made of all nonmetals, so that might be a better way to think of it. And in 1 mole, there are 6.022 times 10 to the 23rd things. 2 times 6 is 12, so you're going to get about 12.04 times 10 to the 23rd. Or if you want to do this, the scientific notation right, 1.204 times 10 to the 24th. Or to the correct number of sig figs, 1.2 times 10 to the 24th, because there are only 2 sig figs in this particular measurement. Letter C, atoms of oxygen. So now this one's the trickiest because it's not on here. I know it says atoms right up here, but we already have the formula units of it right here. And so we'll write that down, 1.2 times 10 to the 24th, formulas of CaCO3. And inside of this, we want to know only those guys right now. We want to know the oxygen atoms, because inside of this box, there's 1 formula unit of CaCO3, 1 of these, but there are 3 oxygen atoms. So notice where I got this ratio, or this fraction. I got the formula units in a position where it's going to cancel, and then I put the atoms that are inside of this formula right here as my new set of units, or my desired species that I put on the top. 1.2 times 3, I think that's 3.6 times 10 to the 24th. That would be atoms of O inside of here. That's the third thing to learn. Pause the video now if you want to re-watch or type me a question. Next one is empirical and molecular formulae. I think we're up to the 5th thing to learn right here. I'll put a 4 right up here. Empirical and molecular formulae, we learned back in chapter 2. We said that an empirical formula is like the simplest whole number ratio between 2 things. And then the molecular formula would be like the exact number or the whole number. You can see how this is reduced to become the empirical formula. Well, here's an empirical formula mathematical problem. In this one, we're given we have ethylene glycol that has a molar mass of 62.1 grams per mole, and its percentage composition is 38 carbon, 9 hydrogen, almost 10, 51 oxygen. Here's the steps. Step number 1, start way on the left-hand side outside the red line and organize your data. And assume 100-gram sample of the substance. Skip a line. Assume 100-gram sample of the substance. and skip a line, 51.6, assume 100 gram sample of the substance. Since you're assuming 100 grams of this stuff right here, that means you have 51 grams of this, 9 grams of this, 38 grams of this. Step number 2, after you assume the 100 gram sample, is to convert to moles. So put grams in a position where it's going to cancel. Moles is your new set of units for each one of these. That's why you organized it so nicely. Now look on your periodic table and look up the atomic mass for carbon, 12, hydrogen, 1, oxygen, 16, and put those in a position where it's going to cancel. 1 and 1, 1 and 16. Now you got a little bit of fancy work to do on your calculator. So 38.7 divided by 12 ends up being 3.22. The 9.7 divided by 1 ends up being 9.7. And the 51.6 divided by 16, that ends up being 3.225 again. Now, once you've got these numbers and you've converted to moles, now you divide by the smallest. Look at these numbers and decide which one is the smallest and divide them all by the smallest number. So we divide every single one of these by 3.225. Make some of the division pretty nice. Those two ends up being carbon, 1, oxygen, 1, because those are the same. 9.7 divided by 3.225, though. Whoops, 9.7 divided by 3.225 is going to end up being pretty close to 3. And lots of times you get some big long decimal here, but it's pretty close to a round number. And so we're given that we have 3 hydrogens in this. And so our empirical formula is C1O1H3. Doesn't matter what order you write them in. And now we can compare this to the molar mass and decide whether this is the molecular formula or not as well. Remember, we can add this empirical formula mass up, multiply it by some number, and that's got to equal the molecular formula mass. So let's add that up on the periodic table. Carbon is 12, and, carbon is 12 plus our oxygen is 16 plus 3 for the total hydrogen, that's 31. So our empirical formula is 31 times some number x is equal to our molecular formula, which is 62.1. Oh, it looks like it's going to turn out pretty nice, right? You're going to end up with x equaling to 2. You have to multiply each one of these subscripts by 2, and then you end up with C2O2H6 as your molecular formula for ethylene glycol. All right, pause the video now or rewatch if you need some questions about that. Type me or send me a question if you're not sure how to do one of those. Last part, toughest thing to learn in the whole chapter is stoichiometry. Stoichiometry has 5 steps. Step number 1, write the balanced equation. Step number 2, when in doubt, convert to moles. Step number 2.5, if there's more than 2 reactants amounts given, divide by the coefficient. The smallest limits. Then step 3, use the mole-to-mole ratio to determine whichever substance you want. And lastly, step 4, convert to the asked for units. So let's put these off to the side right here, and then let's go through one sample problem right here where I go through all 4 steps, and I'll toss in a % yield too, in case you're not sure what that is, because you might get asked one of those problems on the test or on the quizzes as well. So first of all, we're given that 16 grams of oxygen react with 8 grams of hydrogen to form water. And we want us to calculate the limiter, the moles of water produced, and the % yield if 9 grams of water is produced. So step number 1, write the balanced chemical equation. So we know that it's H2, and we know that it's O2, and we know that it's going to produce some H2O, but that's not balanced. 2 and 2, 1 and 2. Uh-oh. I need a 2 here, which means I got to have a 2 here. So that's step number 1 done, write the balanced chemical equation. Step number 2, convert to moles. So I'm given 16 grams of oxygen. I'm given 8 grams of hydrogen. Put a multiply sign in a line. Put a multiply sign in a line. Look them up on the periodic table. Oxygen is 16. Notice that there's 2 of them. So 16 times 2 is 32 grams in 1 mole of oxygen. For hydrogen, it's 1, and then you have to multiply that by 2. So there's 2 grams in 1 mole of hydrogen. So 16 divided by 2 is 0.5 moles of oxygen. 8 divided by 2 is 4 moles of hydrogen. Now I have to take my 2.5 step right here and decide which one is the smallest. So I divide this one by 1, divide this one by 2, and it turns out that you don't really actually have to do the math. You just have to decide which one would be the smallest when I do this division. 0.5 divided by 1 is going to be smaller than 4 divided by 2, so my limiter is O2. So that answers my first question. And notice, even though I had more grams of oxygen to start with, it still ended up being my limiter. Step number, or problem number 2, calculate the moles of H2O produced. So now that I've done step 2.5, I can go to step 3 and use the mole-to-mole ratio. And I always want to work with the given amount of my limiter when I'm answering these problems. So 0.5 moles of O2, multiply sign, put a line. Put your desired unit on the top. I want to know H2O. Put the unit that you have in a position where it's going to cancel, and I have O2 right here, so put O2 here. Oxygen has a 1 in front of it, water has a 2 in front of it. 0.5 times 2 gives me 1, so I'm going to make 1 mole of H2O. Done with part 2. Part 3, what's the percent yield of water if 9 grams of water is produced? Well, I'm going to have to do step 4 to do that, because the asked for units here to find my percent yield are grams. So I'm going to have to do step 4 right here. I have 1 mole of H2O produced, and I have to go from moles to grams because I want to know how many grams of water are actually are supposed to be produced according to math. So add water up on the periodic table. Hydrogen's 1 times 2 plus 16 gives me 18 grams in a mole. 1 times 18 divided by 1 is 18 grams of H2O that are calculated theoretically to be produced. I'm running out of space right here, so I'm going to move